video is a walkthrough of how to use Vivado, and especially using the Xilinx University program gates, and how to work with your project and simulate and put it on a board. So we'll just touch on a few topics, see how it goes. No real planned path here, so it may take a while, so this might be a long video. So obviously put it wherever you want, but again, don't put any special characters in here, no pound signs. I have void spaces. If you want a space, instead use an underscore. Don't start anything with a number. Definitely don't use a pound sign because that does all sorts of bad things in Vivado. So give it a name. We want an RTL project. You don't have any sources, so there's nothing to add. And then we'll just go on. Choose your right board here. So find your board in here. If you don't know if you don't have a board yet, find a board that you can plan on getting. If your board doesn't show up in the board list, then select the part that goes along with that board, and that should be fine. The board packages really just choose the right part for you. All right, so quick interface, nothing too crazy here. But if you go to IP, actually, if we go to settings for the product manager, you go to IP, and you can do the repository. This is where you add the Xilinx University program libraries. So mine are stored here. The basis 3 directory, and then you have XCP and XCP. So you'll have something that looks like this. I have 2 different versions, depending on how recently you grabbed your library files. We'll choose the more recent. It tells you, hey, we found these things. Sometimes it gives you a slight error here, depending on what names you have for your directory structure. Generally, they're going to be okay with the warning or error right here if you see one. All right, so that now allows us to create a block diagram. I'm going to rename this just to make sure that there's a new name in there so we see that carry through our design. So you have this empty diagram window. This is where we can draw our schematic. And now that we've added the Xilinx University program gates, we'll see them here. So if you don't see the gates here, that means you either didn't add your repository correctly, like you add the wrong directory, or you have the wrong board selected that doesn't support these gates. So like Nextdoor has 2 and has a whole bunch of them. We will take I think we'll take an Nextdoor, and you just drag it on, and there you go. So we have one of these. You can zoom in and out using the scroll wheel with pressing Control, and then you can move it back and forth. Generally, Xilinx or Vivado tries to align things up for you, so I don't do too much here to make things pretty. But let's say we wanted to have a 4-bit bus come in. We will compare all 4 bits together to see if they all match. If they all match, we'll produce an output of a 1 and a 0 if they don't match. In addition to that, let's take in that bus of 4 and return like the inverse of that. So nothing like extraordinarily useful for like the real world, but we'll cover on a lot of topics. So we want to create a port and we'll call it input. And we will say it's a 4-bit bus. So 3 down to 0, there's 4 bits there. It's an input type. It's technically data, so we'll go with that. Yes, I forgot input is a taken term. So we'll just call it X. X is good. All right, so you can see 3 down to 0, that is the size. And we can move it a little bit. And you press the regenerate layout, it will go and move it somewhere else. But let's say we want to grab an individual bit on here to put it into our XOR gate. For that, you want a slice. There you go. So here it's saying you have a data bus in of 32 and you have a data bus out of essentially 1. So just like 31 down to 0 is actually 32 bits because you get to count 0. The output is also not just 0 bits, it is a 1-bit output. So if you double click on it, you'll see that 32 in, out is 1. So if we change this to 4 in, that means we're going to go down 0 to 3. And it says over here, we can grab, like if we wanted to grab bits 3 and 2, it would look like this. So that would grab 2 bits. And there you go. See, the output is going to be 2 bits. So if you want to just grab bit 2, it would be like this. And it would just be an output of 1. So unfortunately, the slice doesn't like show you great things on here of which bits it's grabbing. So you really need to go in and click on it to find out what it's actually doing. So for this case, we want to grab the most significant bit. And then we'll grab the other ones as well. So we'll copy that. So actually they've got some good default names there that we can give, 3 and 2 and 1. That'll at least give us some idea of which one's which. So this one should say 3 down to 3 inside of it. It does. This one we want to say 2 down to 2 to grab bit 2. Again, bit 2 is still just 1 bit wide. This one we want to be 1 down to 1 to be 1 bit wide. And this one we want 0 down to 0 to be 1 bit wide. And there we go. So we can run this to all of these. And that's going to take X as an input, and it's going to take in each individual bit and slice it out. And we will then have a single bit output. So this is going to compare these 2 bits. So in XOR, we'll compare 2 bits, and there's an XOR. We'll go with that. XOR will tell you if one or the other is set, but not both. And an XNOR will tell you if if they both match. So you can go and look at your truth table. But if 0, 0, or 1, if the input is 0, 0, or is 1, 1, then it will produce a true on the output. So XNOR is great for determining if something matches. So we need to know if those match. We need to know if those match and those match. So basically we'll make sure those match, and we'll check these. So if these match and these match and these match, then all of them match is what we're going to do. So in order to do that, we need to do an AND on the output of those. There's a 3 input AND gate that happens to exist, so we'll line that up. we go. We now have an output that we can create. So we can create a port, call it an output data. We can just call it result. If you press the regenerate, it will try to make things look pretty. It did a fairly decent job of that there. So we also wanted to produce an output bus just to show how that would work. So create port, reversed. So you want all the bits in this to be backwards from, how the input was. So still a 3-bit wide bus, but we want to put it back together in a different order. So concatenate, which is often even concat, will take multiple things and put them back together. So you can have a number of ports in as 1. All the inputs are 1 bit wide, and the output will be a 4. So these are all on auto, so it will kind of figure things out as you supply to it. So bit 0 is what in 0 is. So if we want to reverse things, we would connect bit 0 to x3 and bit 1 to x2 and bit 2 to x1 and bit 3 to x0. So this will put everything back together, and its bit 0 inside the concatenation will actually come from bit 3 of x. So everything should be completely reversed from where we started. So you hook that up. You can press the make things look pretty button again. And again, it does a decent job. It's fairly compact, and you can see where all the wires are going, which is the key. All right, so everything's looking good here. We did a bus input. We split it up into slices to take individual bits out, put those into some gates, got a single bit result and a reversed ordered concatenated output as well. So all of your basic building blocks are here. So you press Control S to save. Anytime there's a little asterisk somewhere, it means it isn't saved. You want to probably stay on sources as much as possible. If you look at design sources, there's not a lot going in there right now, and that's because we haven't done much. So right click on this, and you can create an HDL wrapper. HDL wrapper will be you let Vivado auto deal with it. HDL wrapper is the Verilog file that will describe the diagram. You can see this window over here is going through multiple refreshes. This will and that will create a hierarchy that shows the design. So inside here, it should say it's a wrapper file, and inside it is instantiating a top block diagram as this. And everything seems to be okay in there. Here we want to generate output products. You want to choose as many jobs as possible. That will choose as many cores of your computer as possible. So it will run slightly faster. It can't run. It can't run like 8 times the speed of your original. Like if you just chose 1 core versus 8, but it does a decent job of going fairly quickly. All right, so whenever there's the spinny circle up here, that means something is running. You can see how it's doing and what it's doing perhaps by looking at design runs. And you can see top module is going through and doing some things. And it's essentially processing the XNOR gate for us. So could be because I chose the new blocks here. I haven't chose those in a while, so those might be taking longer to run. But you can see the elapsed time is fairly significant. going to go over and check on my processor usage, see what that looks like. Yeah, Vivado is running according to my processor, so these are our real tasks. We'll stay with it. So up here, when things are correct, your top block diagram wrapper should basically have a hierarchy underneath it that has the block diagram underneath it. So if you click the caret right now next to top block diagram, the yellow one is always like the schematic here. You'll see that .v is underneath it, which is the internal Verilog of that diagram. And then the top block diagram wrapper should be the thing that is above in the hierarchy of the top block diagram. And in this case, it is not. So we're going to go and click on Move to Top, which will mean that we're going to force this to be the main element of our design. And since it calls top block diagram, it should reorganize this thing. And for some reason right now, it is fighting us. So you can see down here, all the runs are complete. We're going to create an HDL wrapper again, just to make sure we didn't do that out of order. Okay, there we go. Sorry, I was in compile order and you should be in hierarchy. That is the problem. So if we look at hierarchy, we're doing fine. Everything is in a hierarchy. If you're ever over in compile order, it will look like this, which I was accidentally in. So sources hierarchy will show you, how things are in your design, and also the bold thing is the thing that it will actually create when you run the synthesis. So if you double click on these, we saw that in the slices there wasn't a whole lot going on, but in the gate there's this delay. So the delay is there to try to represent real electron flow, how quickly electrons can actually pass through certain systems. So there's an actual delay that occurs when that happens, which is great for like real life scenarios if you can do that well, but could interfere with what we're doing as part of our time here. So if you know what delay is and you want it in there, then choose it to be in there. The default delay is sometimes not what you want though. So you might want to zero all those out. Anytime you make a change to your schematic, I recommend recreating your HDL wrapper. You'll see it's updating this time because that's new, and regenerating your output products. Just to make sure that you enter a synthesis with the most likely chance of success. So yeah, it might go out and do something, which is fine. That will take a while. So with these three lined up like this, we're doing fine. If you come down to simulation sources, you see the same thing. So if we were to synthesize right now, it will synthesize what's in bold underneath sources. And if we simulate, it will simulate what's in bold under simulation sources. So for synthesis, that's great. We're going to create this design, and we're going to turn it into a system that can eventually get put into a device. For simulation, we don't really want to simulate this schematic, because simulating this schematic is pretty boring, because without inputs, the schematic we won't know how it will behave. So we have to provide inputs to it, and we do that through a test bench. So while all this other stuff is running, we'll add a source. If you right-click on simulation sources and do add source by right-clicking, it will actually default to create a simulation source. Let's see, a bunch of things you can do in here. You can add a file, you can create a file. So we'll create a file called, top block testbench.b. So you never want this name to match any other name in your system. If it's the same name, then Vivado could get confused, and also you could get confused, both which would be bad. So you can click finish. It asks you to, hey, do you want to fill this thing out? I find this will try to auto-generate some code. I always find that the auto-generated code isn't that useful, so we'll just click OK, so it clears out. All right, so well, we see that the regenerate output products is done, so we will run our synthesis, and we'll see that running down here because we're on the design runs area. And over here we have a top block testbench file that's been created, and it's got everything in here. We're gonna get rid of the comments just so it's easier to see. This character right here is the character next to the 1 on the keyboard. This is 1 nanosecond and 1 picosecond. The 1 and the L can often be pretty indistinguishable in Vivado. Fortunately, I installed some good font packs to make sure that it works okay here. All right, so this is the architecture of a test bench. And again, when we're done, we want this to be in bold and our wrapper to be underneath our test bench. So we're going to simulate our test bench, and our test bench is going to have a wrapper inside of it. So this creates a test bench, and it's called this. So I mean, you can name it differently than your file name, but that's usually not a good way to go for you to have good organization. So that's the name, and then we can create some inputs, some layers, and some registers to hold data. So if you want to hold a piece of data, it goes in a register. So since this is done, we can implement now. We're going to pause and go and look at the simulation first. So if you want to hold data, you need to put it in a register. We're going to hold a piece of data called like X input. And this is our bus. And when you're assigning things in Vivado and you want to make a bus, you have to actually put the bus size before the name of the bus. And then, so this is the data we're going to give to our schematic. So we need to change that data, which means we need to hold information in there inside the simulation so that we can give it to our schematic. And then our schematic's going to give us two things out. It's going to give us our reversed bits, and since we're not going to change that inside the simulation, we're going to have the schematic change that and give us that data. That's a wire. So anything that isn't holding data inside this container is a wire. It usually means we're just transporting between two spots, or we're just taking it in and viewing it internally. And then we also have a wire that's called like matching or something like that. And that's just a single bit from our schematic. Okay, so we made our three things, and now we need to link those up to the schematic. So we need to call our schematic, and our schematic is essentially like a data type in the equivalent terms of programming language. So if we want to use our schematic inside this test bench, we need to make one of them. So you can make more than one. That's more of an advanced discussion. You can make multiple of them and like have them interact and link together. Once you're kind of done playing around in the diagram phase and writing more Verilog code, that will be a place to go to. But you can give this whatever name you want. So map diagram 1 kind of thing. So this is the name. So this is like a variable name from programming language. So data type, variable name, if you need to think about that to get started. But this is the name of our schematic wrapper file. So this is the Verilog container that we want to create one of. And then this is the name we're going to give it. So the name doesn't really matter for us in this case because we're not doing anything beyond this simple simulation. But as you get multiple of these designs together, then you'll have to like communicate between the two, and then that's where you would use the name. So there are multiple ways to link things up. The best way to link things up is to use the dot, and then you take the dot and you come over and you look at your diagram, and whatever name it is in here, that's the name that should be after the dot. So in here we have a capital X. We want to link that up to what we called X input inside our container. So dot schematic name, but really it's dot whatever this is name, and then in parentheses whatever we want to call it here. So this is the simulation file name, which can be different. In simple simulations, they're probably pretty close to the same name, but as you again get more advanced and like link things together, they obviously can't be the same because you're gonna have multiple of the same thing. We have reversed and result, both lowercase, that we also can use. So reverse and result. We call it matching over here. And finish off the parentheses, and then semicolon. And now you've made one of them. So we do initial begin. Anytime you see begin, it's essentially a curly bracket from programming, so you can kind of think of it as initial begin, and then end is that. I mean, that's kind of what it is. So kind of like that. So you want to take all your inputs and set them to their default state. So in this case, X input is a bus, so we can just treat it as a decimal number, and we can set it to 0. You can set these to binary or hex or whatever you want. If it's a single input, you can set it to a 0, 1, like a 1-bit number. And then if you want to change values, so in this case we want to cover all possible values of X. Since we have a 4-bit input, all possible values of X will be 2 to the 4 or 16 numbers. What do we want to have happen? And we'll just increment it through all the possible combinations. So this will always occur. That's why it's an always. Every 20 times time segments, it's going to increment X by 1. When it gets to 15, it will try to add 1. It will run out of bits, so it'll go back to 0. So we'll just kind of rotate through everything. You can also finish this off, but the default should be good enough for us here. So we save this. If you watch while we save it, it's refreshing over here, and now you're seeing down here it's doing a couple refreshes, but it's already looking encouraging. The top block TV is now at least hierarchical, the first thing in this list. It hasn't turned bold yet, which is a concern for us. So we'll watch for that. So it's still bold right here. If you ever see that the schematic is still bold, that's a problem. We'll see what the result of this issue is, and we'll just give it a try. So we're going to run the simulation. Again, this simulation is only going to occur on our wrapper file, which is essentially our schematic. So if you simulate your schematic, you generally will see a whole bunch of blue and red lines on the simulation. And here we go. Best button in the world in the simulation is the zoom fit, and it will just zoom out for the entire time scale. And we'll see blue and red lines. So our input is X to the schematic, and those are all blue. They're all high impedance, which essentially means undefined in this state. And then the output is a red and also a blue. So the result is saying, hey, I can't give you an answer because I don't know what the inputs were. So don't know. And then the reversed are all high impedance because those those essentially just pass through our schematic. So close the simulation. We did something wrong. We know what we did wrong in this case. We only simulated the schematic, but when you see blue and red and only blue and red, that's the reason, most likely. So if you right click on the simulation and you say set as top, then it will go through and say, all right, you want to simulate the Testbench file. We see it in bold there. And now when we run simulation, we'll run a simulation on this Testbench that we just wrote instead of the schematic. And of course, doing this live, I did something wrong. Oh, what did I do? So yeah, it'll give us a decent chance to figure out errors. So if we come over to TCL console, it gives us all these red errors. Generally, those red errors are not useful, and we're looking for the errors above that are in black. So in black, we see two errors, and it says cannot find port reversed on this module on line 9, which means we essentially spelled this name wrong, probably, and we're going to go check it out. So if we look at the diagram, we have reversed with a D. Hopefully, as you were watching that, you saw that and realized that I had misspelled it. So we fix that up, save it, run the simulation again. That is a common error. That's a common error when you're doing other programming as well, you know, when you don't get a name quite right. But that's how you observe it here. All right, so we can see a bunch of things going on here. The zoom fit went further out than what we wanted, so we'll zoom in a little bit, and we'll see that we started at 0 because we told it we're going to start at 0. And when we're at 0, all the bits match because we have 0, 0, 0, 0. If you want to see the individual bits, you press the caret next to it, and you can see all the individual bits are matching, so our output is a 1. And if you want to look at whether or not we reversed the bits, we did. You can click here and you can just see all the values. Here we reversed the bits, so we were 0, 0, 0, 1, and now we're 1, 0, 0, 0. That's not matching. Our input is going from the decimal 0 through 15, and then it will reset. And you can see all the bits get reversed. And then we can have another true when all the bits are 1 when we get to 15. So kind of did everything you would need to do there to do a simulation. So that covers schematic, Xilinx University program, schematic symbols, how to make a test bench, covered buses, and how they show up in here. You want to initial begin basically everything that's a register. So you put that here. You can use an always block to have them all move around, or you can do another like initial begin and say at certain time segments you want things to happen. And they all build off each other. So we can say at #20 I want x input to equals x input plus 1. We don't have more than one thing, so we'll do that for 4 times. So we'll go from 0 to 1 to 2 to 3 to 4, and then on the last one we'll skip to 15 and then just stop essentially. So this is every 20. So if we want to see every 20, every 20, every 20, and then we'll like wait, and then we'll go to 100 after 20, 40, 60, 80. So at 180 time cycles, we will go there. We'll click this button, see if it yells at us. Yeah. So it automatically closed it. If it gives you an error message, quite often it's because you didn't close it, and that would be the blue bar up here. So this simulation is running when this blue bar up here is running. If you get an error message related to the simulation file, like some files like locking it or something, it probably means you just need to close the simulation manually. All right, so we said at #20, so 20 time units, we were going to increment x by 1. We did that. Everything kind of follows what we did last time. We incremented by 1 after 20 again, incremented by 1 after 20 again, increment by 1 after 20 again. But then we waited here for 100 times cycles, and then we set it to 15, or in hex F. And then it just stays there for the rest of all time. You can see F just right there. So that's how you would do it if you wanted to do a simulation manually by changing individual things. So once you're done, you would generate run implementation. Again, when this comes up, you want to click, do the most number of cores possible. I've already selected that and said stop bothering me, so we didn't even get that window. Once implementation is done, then you can go in and choose your pins, and then you would generate your bit stream. So that's generally how it goes. Hopefully that helps someone, if you missed a spot somewhere when you were learning how to go, or you were just at a good position that you could watch this and understand where we're how to do things. Yeah, maybe I'll make another one of these, but this is a good intro.